So welcome everybody to this week's session of the synthesis workshop at the Simons Institute. Again, we'll be continuing the theme of exploring the connections between formal synthesis and machine learning. And today's session will particularly focus on theoretical aspects of that connection. I'm pleased to introduce our first speaker, Susmit Jha, who is a principal scientist at SRI International. Susmit has done some of the foundational work on program synthesis and formal synthesis over the past 15 years, for which he was recently recognized with an ICSI Test of Time Award. Let's just dive in straight in. Susmit is going to speak about Oracle-guided learning of compositional concepts. Susmit, thank you for being here. Take it away. I think you're muted, Susmit.
Thanks, Sanjit, for a very kind introduction. So as Sanjit mentioned, I am Susmit. I'm a principal scientist in computer science lab at SRI. Today, I'm going to talk about formal synthesis, Oracle-guided learning of compositional concepts. This is a joint work with Sanjit and a number of collaborators over several years. I would like to acknowledge all their contributions, as well as I would like to acknowledge my employers, Intel, Raytheon Technologies, and SRI, and different funding agencies which have enabled me to do this work over the last decade. So what is formal synthesis? Formal synthesis is essentially a process of learning a compositional concept, satisfying a high-level formal specification. Now, examples of such compositional concepts include programs, controllers, explanations of machine learning models, inference of intent of AI agents. And compositionality is key here because this is what enables us to exploit automated deduction and makes formal synthesis no longer just a machine learning problem. And over the last decade, we have applied formal synthesis to a wide spectrum of applications, which include program synthesis, synthesis of controllers, finding explanations of machine learning models' decisions, as well as inference of intents of AI agents. We've also used it for a fun application where we were able to automatically generate completely new magic card tricks. Obviously, we will not have time to go over all of these applications in 25 minutes. So my plan is to go over some key results which I thought might be of interest to this particular audience. So I will begin by presenting a unifying view that describes formal synthesis as essentially an interaction between Oracle and learner, both of which are co-designed for a target concept. And this is one key differentiating factor between formal synthesis and machine learning, where often oracles are expected to be frozen, while in formal synthesis, we try to design the learner and the oracle together. Secondly, I will talk about theoretical characterization of different formal synthesis techniques, where we consider oracles and learners with different properties with different powers. And then I will go over 3 applications. The first will be the program synthesis work, which was the first paper on this topic that we had at ICSI 2010. And then I will talk about how to use this method to explain AI decisions based on our paper in the Journal of Automated Engineering at 2018. And then I will talk about how to use it to automatically generate robust control policies, which was published in Alert and Control 2018. So what is formal synthesis and why do we need it? If you think about induction, induction refers to inferring general rules from specific examples or observations. For example, if we are given a bunch of images of digits, as you see here, we could, from these examples, infer that the rule being followed is that all the numbers that we are going to see are going to be greater than or equal to 7. On the other hand, deduction is about applying general rules to derive conclusions about specific instances. For example, if we know that all the numbers that we are going to see are greater than or equal to 7, and if somebody shows us this occluded image that you see here, then we can infer that this number is 8 and not 3. Formal synthesis, in contrast to induction and deduction, is about simultaneously learning from data and deduction from rules. So if we are given a data set which has these corrupted images, where some of these digits have been partially occluded, and we know that the rule that all numbers that we are going to see are going to be greater than or equal to 5 holds true, then based on this data set, and this rule that we know is going to hold true, that all numbers will be greater than or equal to 5, we can actually infer that the tighter rule would be that number is greater than or equal to 7. And this is a very sort of like toy example of what formal synthesis can do. And this formal synthesis is essentially an instance of what we call induction, where we combine induction and deduction using structural constraints. Now, this example might appear very concocted. So let me present an application which is in a much more realistic setting, but along the same lines. Here we are looking at nuisance dataset, which is a standard dataset in machine learning, which comprises essentially road images from Boston and Singapore. What is interesting about this dataset is that it's highly imbalanced dataset. So it has a number of images of humans, cars, trucks, and movable objects. By movable objects, you will essentially see these road cones. But it has very few examples of bicycles and motorcycles. And secondly, many of these images, many of these instances are occluded, which makes this a really challenging dataset to work with. Now, if we apply purely machine learning, in particular deep learning, then the overall accuracy that we observe is around 88%. But for those classes where the number of instances is really small, the accuracy drops down to 57% and 61%. Further, as we look at those instances which have higher occlusion, the accuracy drops down very severely from 57% to 12% at 30% occlusion for bicycle, and to 2%, 2.36% for occlusion of 50%. But if we use formal synthesis for perception, then first, our overall accuracy goes up because we are able to incorporate spatiotemporal rules of co-occurrence of different objects in our scene. It goes up from 88% to 95%. But even more significantly, our accuracy goes up on those instances which belong to class where the number of examples that we had in the dataset was small. For example, if you look at motorcycle, it goes from 61% to 73%. Further, the improvement is even more impressive when we look at instances where we have occlusion. So this gives us a much more convincing argument about why combining learning from data and rules, for example, as we do in formal synthesis, is going to be clearly much more advantageous compared to just doing learning from data. Now, the next question would be that why do we need it to be article guided? Why can't we assume that all the rules and symbolic specification available to us are directly given? And we don't need to essentially think of it as an article. We can do white box analysis, automated deduction on it. Then, well, the first reason is that even when symbolic specification is available to us, it may not be amenable to deduction. Two examples that come to mind right away would be first, deobfuscation. Let's say that we are trying to use program synthesis to deobfuscate code. Now, obfuscation can make programs arbitrarily difficult for static analysis and automated deduction. So thinking about deobfuscated code as a white box symbolic specification may not be quite workable hypothesis to design a technique with. Similarly, with neural networks, even though they are symbolically available, they are just too large to be amenable to automated deduction. The second reason is that sometimes the specification may not even be available to us in a symbolic form. For example, maybe we are interacting with humans, which have some notion of what is right and wrong, but they can't put it down in a formal property. Or we could be interacting with nature or complex physical models. And these are the reasons why we are thinking about capturing specification, not necessarily as a white box logical form, but rather as an oracle, which is amenable to some forms of analysis and typically lightweight automated deduction. Now, to make our approach more powerful, we obviously need to design the oracle, which will be capturing the specification in a way that it supports particular interfaces which are of interest to us. In some sense, you can think about this as saying that what are the automated deduction questions that we can ask on this particular formal specification, because it's no longer available to us as a white box, but is rather available to us as an oracle. And here you will look at some examples of what these interface queries can be. Obviously, positive witness queries, these are examples. This is what traditionally machine learning has been about, that given a concept, give me example of instances which satisfy this concept, which belong to this concept. The second could be negative witnesses. We are going to ask the reverse question that give me instances which do not belong to this concept. The third would be membership query, where you can pick an instance and then ask an oracle that does this instance belong to this particular target concept or not. The fourth would be equivalence query, where you come up with a hypothesis concept and give it to the oracle. The oracle can either say that, yes, this is the target concept, or come back to you with a counterexample. The next could be subsumption or subset queries. We come up with a hypothesis concept, a proposed concept, and then the oracle would come back and say that either the target concept is a superset of this particular proposed concept or give you a counterexample. And the last would be the distinguishing input, where the learner could come up with a concept and the set of examples used to form that concept. And the oracle would either find an alternate concept which is consistent with all these examples but differs from the proposed concept in at least one instance, or say that, well, it has no such alternate hypothesis, at which point learner can be sure that this is the single hypothesis which is consistent with all the examples it has seen so far. Now, what Oracle-guided formal synthesis does is that it takes as input a concept class and an Oracle interface between the learner and the Oracle. And again, to emphasize, the Oracle could have the logical specification and the data available to it, based on which it would be able to provide responses to the learner. And then we have a notion of a dialogue. A dialogue is essentially a sequence of query response which conforms to this particular Oracle interface. An Oracle-guided formal synthesis algorithm is a pair of learner and Oracle, both of which are being co-designed, where learner is going to be a non-deterministic algorithm that will map a dialogue to a concept and a query. And an Oracle is going to be another non-deterministic algorithm, which will map a dialogue and query to a response. We'll say that an Oracle-guided formal synthesis algorithm solves a synthesis problem if there exists a dialogue between the learner and the oracle, such that the learner converges to the target concept. Now, this can be viewed as a generalization of query-based learning, which has been around for at least half a century. And in particular, there are two lines of work which are very relevant here. One would be the gold style learning of formal languages, which has motivated a lot of our theoretical study of formal synthesis. And the second would be learning from membership and equivalence queries by Dana Englund and others, which has motivated our work on program synthesis. But in contrast to query-based learning, here the Oracle is not a frozen entity which only provides examples or provides responses to some particular kind of queries, but rather we have extended this notion of Oracle to support arbitrary interfaces, which allows us to exploit domain-specific advances in automated deduction, where we can utilize knowledge from program analysis, control theory, to be able to design much more richer Oracle interfaces than providing only examples or responses to, let's say, membership queries. So if you look at even the query-based learning, one key thing here was that they studied the power of synthesis using different nature of queries, and that has inspired us to look at how we can analyze formal synthesis techniques and look at what is the feasibility of synthesis when we consider learners and oracles with different powers, with different properties. In particular, we have looked at learners which have finite and infinite memory, oracles which have different interfaces. The first would be that they only support counterexamples, arbitrary counterexamples. The second would be that they support minimal counterexamples. That is, they're going to produce counterexamples which are going to be smallest in size. The third is about constant bounded counterexamples, where the oracle is going to produce a counterexample which is going to be of length smaller than some given constant bound B. And this is motivated by work on bounded model checking, context bounded testing, and so on. And the last one is about positive bounded counterexamples, where the oracle is going to produce a counterexample which is going to be no larger than the largest positive example it has seen so far. And this is motivated by work on bug finding methods that mutate a correct execution in order to find buggy behaviors. Now, I will not go in detail about how all of these different oracles and learners compare to each other, but just to point out some of the highlights of our theoretical results. So what we noticed is that for both finite and infinite memory learners, there's absolutely no benefit of using minimal counterexamples with respect to counterexamples when it comes to looking at feasibility of synthesis. Secondly, in case of finite learners, what we found is that having positive bounded counterexamples is actually much more powerful than using arbitrary counterexamples. But for infinite memory learners' case, this is not true. In fact, positive bounded counterexamples are strictly less powerful than having arbitrary counterexamples. Further, we were also able to find a language family that can be learned using counterexamples and minimum counterexamples, but that cannot be learned using a constant bounded counterexamples or positive bounded counterexamples, both in the case of finite learner as well as the infinite learner. And our Atta Informatica paper has more details about all these comparisons. We have identified exactly what language families belong in the intersection and union of these different cases. But here, I think these highlights would probably give you a good idea of what kind of feasibility results we have on the formal synthesis approaches. Now, moving on to some of the key examples of applications of what we have tried with formal synthesis. The first one is obviously the first paper that we wrote on this topic, which was in 2010, the ICSI paper on program synthesis from components. Here, the concept class was programs as a composition of functions. And both the learner and Oracle were implemented as a satisfiability solving algorithms, essentially SMT solvers. And the Oracle interface between both was given by the distinguishing input query, where the learner would propose a program which is consistent with all input-output examples seen so far, and the Oracle would come back and either provide a second program which is consistent with all examples, or provide or say that, well, there's no such a second example available. And then eventually the learner would converge to a single consistent program with respect to all input-output examples, and it would terminate there and say that, well, this is the program that I have synthesized. And we used it to deobfuscate programs. We also used it to generate these bit vector manipulation programs, which even today are used often as a benchmark in program synthesis literature. The second example, which is relatively more recent, but 4 years old now, was about explaining AI models. In particular, we wanted to look at arbitrary AI algorithms, including A star, deep learning models, and so on, and then be able to explain local decisions. That is, given a single decision, can we figure out why the model made this particular decision? And if you think about it, decisions are essentially often made on an input based on only some part of the input, some relevant part of the input, and finding that relevant part is a key part of the problem. Once you have that relevant part of the input identified, then you can do program synthesis, decision tree learning, or even simple Boolean formula learning to be able to characterize the explanation. So here I will focus on finding the relevant variables. Beyond that, you can think of it as a program synthesis problem. So let's say that we have a scenario where the AI algorithm that we are looking at is a A star algorithm, which generates optimal plan given a particular map. Then the learner has a map, which is the current input, and it has ability to be able to mutate this map in arbitrary ways and give it to the Oracle, which will run the A star algorithm and then evaluate some property on it. For example, the property could be that, well, why does the plan have some particular segment in it, or why does it not have some particular segment in it? And what we are trying to do is to find an explanation for this particular property, that why this property held, why did we go through a particular segment, why did we take a particular bridge, for example, or why did we not take that particular bridge? And we designed it essentially as a protocol between this Oracle and learner, and we'll look at more details here, but the key interface between both is given by a simple membership query, where Oracle can give a map of choice, where the learner can give a map of choice, and then Oracle can evaluate the A star's output on that map, and then come back with either saying that the property holds or does not hold. And the same can be done with the deep learning model. For example, let's say that the learner is trying to explain why a particular model which predicts whether somebody should get a loan or not get a loan, why was a particular decision made, what attributes were important for it. And this, as you can see, is very important to be able to understand, let's say, biases in a deep learning model. And one key observation here is that these AI models are often, they make decisions often on very small number of variables. That is, explanations often have a very sparse support. And this is something that we have utilized in our work. So we implemented Learn and Oracle as essentially using, the learner was implementing a Hamming distance search over the inputs. That is, it was finding these mutations of input based on some Hamming distance between inputs. And the Oracle was implemented using a local verifier or an evaluator. And then we were able to show how we can explain results of optimal planning algorithms like A*, explain decisions made by reactive exploration strategy, as well as compute saliency map of images. And more recently, we have shown that these explanations can in fact be used to compute confidence of a machine learning model and detect adversarial examples. And then similar to complexity analysis in query-based learning or the standard teaching dimensions in machine learning, here what we care about is the number of queries that we make to the Oracle. And we were able to show that even though the overall space of possible explanations is doubly exponential in the total number of variables, our approach actually uses logarithmic number of queries in the total number of variables, which makes it much more efficient and practically usable for even deep learning models. And then I will just quickly go over the control synthesis part. I believe I have 5 minutes. Is that correct, Sanjay?
Yes, you have 5 minutes.
Cool. So this is the last application. This is about synthesizing controllers. And here, one key problem is that often when we try to synthesize controllers, it is with respect to some surrogate model. Either it's a set of ODE equations or more recently, these machine learning surrogate models. But we want to deploy these controllers in a real world. And the reason we don't try to generate controllers either using reinforcement learning or classical control synthesis directly with the plant model or the detailed simulator is because these are going to be slow, as well as they are more resource intensive, and they're also more risk prone. Imagine trying to generate a robotics controller by directly interacting with the physical world. It's possible that we'll end up actually destroying our physical hardware. So the key thing here is that, well, we want to generate controller which will work in the real world, but is designed using a physical plant. So we want to minimize the number of interactions we have with the real world while trying to learn these controllers. So this motivated essentially a hierarchical Oracle-guided synthesis approach where we don't have one single oracle, but rather two oracles. The first oracle is the detailed simulator of the plant with which we are going to have sparse interaction, hopefully sparse interaction where we don't query this oracle very often. And the second is the surrogate model, which we have to learn as we are trying to find an optimal controller. And the learner, which is the controller synthesis algorithm, can interact more frequently with the surrogate model. I will not go in detail about the exact interaction process between the two, but the key thing here was that we wanted to use max entropy as our guiding principle to figure out what would be the next experiment we run in the real world to be able to concurrently learn a good surrogate model for a controller synthesis task, as well as be able to design an optimal controller. And then we used it to essentially generate controllers for OpenAI GEM benchmarks using the Mujoko simulator. And what we found is that our approach is able to achieve higher rewards, that is, it has a much more optimal controller, as well as reach it much more quickly. That is, the rate at which we are able to learn optimal controller is also higher than more model-free control synthesis approaches. So in conclusion, formal synthesis is a process of learning a compositional concept, for example, programs, controllers, or explanations of machine learning models. And I showed you a few example techniques that have tried to use formal synthesis in these contexts. And then we looked at a unifying view of formal synthesis as an interaction protocol between oracles and learners. And then we reviewed some key technical results on feasibility of synthesis using different kinds of oracles and learners. So with this, let me conclude. Thanks for a patient listening. Are there any questions?
Okay, thank you, Susmit. Are there any questions from the audience? Radu, do you have a question?
Yeah, I have a question. So one obvious way of having an oracle is the model checker. I think you had an example where or a set solver or whatever. The only question is, whether this really works. I mean, so people use synthesis often because it scales much better than the verification tool. So, do you see any way of, avoiding this problem?
I couldn't quite see the problem here. Maybe let me try to elaborate your question and get to.
I mean, there is no model checker for deep neural networks.
Right, but that is essentially.
So how can you do if suppose I want to apply? Because I would like to have an oracle, my verification tool, my model checker, but I cannot because it doesn't scale up to the size of the deep neural networks.
Right, Radu, but that's where the power of formal synthesis actually comes to bear, because we are not trying to use a predefined oracle. It's not that we are going to pick some state-of-the-art model checker and say that, well, this is available to us, so this is the oracle that we want to use. Rather, we are going to design oracle as part of the synthesis process. So if we cannot do model checking of a piece of code, then the oracle is not a model checker for that code. Rather, we are going to look at some lightweight analysis methods. For example, we could look at methods which do statistical sampling of inputs and learn invariants. That could very well be an effective oracle. So how do we pick the lightweight automated deduction approach, which we can run on this class of problem, is going to determine what oracle we use. So for example, for neural networks, we have done work where we try to find explanations of neural networks. Here, we don't need to run a global verifier. All we care about is that can we do local robustness checks that is available to us. In fact, in our earlier work, which was the NFM 2017 work, we didn't even need to do any sort of verification. We could just evaluate the neural network model on specific examples, which is the simplest sort of queries that you can design. So I don't think we should look at it as an approach where we have these predefined oracles or verifiers available and we are trying to use those existing verification tools or model checking tools to do synthesis. Rather, we are trying to figure out what is the kind of deductive queries that can be supported in a given class of problems, and then design a synthesis method which only uses that oracle interface, which comprises using this lightweight deduction process. Does that answer your question, Radu?
Yeah, absolutely. So any lightweight tool that is suitable, symbolic.
Right,
tool.
and this is the key question, right? Like that, how do you separate what is an easy deduction question and what you need to solve using induction? And if you think about the entire technique of formal synthesis, it's trying to essentially say that the boundary between these two is something that we should not predefine. This is not that we have the best deduction approach available out there and the best machine learning tool available out there and we just club them together, right? It's not going to work. If we take model checkers and we take some best deep learning algorithm and club them together, they're not going to talk to each other. What we want to do is to think about, for a given target concept that we are trying to synthesize or learn, what is the best, what is the sort of like most resource efficient, most effective deduction approach that we can design for it. And then what would be the corresponding inductive approach that we need to design to be able to couple them both together.
Thank you. Very nice.
Sure.
There's another question in the Q&A from Abhinav Verma. The question is there a possibility that you could leverage machine learning techniques in creating the oracle as well?
That's a very good question, Abhinav. Yes, definitely. I think we have worked together and we were looking at the problems where we were trying to design oracles using machine learning models. What we think as induction and what we think as deduction is not as sort of like the demarcation is not as clear as often we think it to be. So definitely some deductive approaches themselves could use induction. And if you look at our work on hierarchical OJs, this is one way to get in that take a step in that direction. That we don't think about induction and deduction as two entities which are talking to each other, but rather this is a recursive process where the oracle itself could be implemented using an oracle learner couple, which itself could then recurse down. I hope that answers your question.
All right. Thanks, Susmit. Perfectly on
Thanks,
time.
Nitin.
So let's move to our next speaker. Sandra, can you go ahead and share your screen?
Sure. Thank you.
Okay, while Sandra's doing that, let me go ahead and introduce our next speaker.